What if the most beautiful natural building material we have could be made fire compliant to the highest standards? For decades, we've been told that we must make a choice between fire safety and timber, performance and sustainability. At Abodo, we ask the question, can we fundamentally reinvent timber? This question led us to Varro. My name's Ben Campbell, and I'm Head of Innovation at Abodo Wood. In this presentation, I'm going to give you some insight into the development journey that we have taken in creating this groundbreaking product. But first, let's have a look at what Abodo stands for and where we've come from in getting to this point. Our mission is to protect the world's irreplaceable old-growth forests through innovation in timber. We make a clear distinction between old-growth forests and new growth. Our position is that we should leave the world's ancient old-growth forests standing, because once we've cut these forests down, these ancient ecosystems won't be replaced in the way that they once were. In contrast, new growth, rapidly renewable plantation forests take a fraction of the time to grow and present a fully sustainable, renewable building material. Our focus is on producing what we call new growth feature timbers. These timbers come from highly sustainable, renewable plantation radiata pine forests in the central North Island of New Zealand. We use 25 years of innovation to apply technology and know-how to the sustainable base material so that we can provide alternatives to old-growth species in high-performing timber applications in exterior situations. In doing this, we enable designers, builders, and end users to realize their design aspirations without disadvantaging future generations. Abodo is located here in Aotearoa, New Zealand. We're a New Zealand-owned business, and most of our operations are located in the central North Island of the North Island of New Zealand. We also have a showroom in the South Island in central Otago and Cardrona. And here we have accommodation where you can come and stay if you'd like. So starting with the forest. Our sawmilling operations are located right next to the Kaingaroa forest in the central North Island of New Zealand. The Kaingaroa forest is the largest plantation forest in the Southern Hemisphere. And you can see in the photo here, a photo of the log truck that's coming out of the forest and goes directly into the mill gate right next to the edge of the forest. All of the timber that we source comes from FSC certified forests. The Forest Stewardship Council is the gold label in forest certification worldwide. It provides a chain of custody from the forest through the sawmill and to the end user to ensure that the timber comes from well-managed forests, but also at least 10% of these forests must be kept as native forestry, which encourages biodiversity in these forests. One great thing about radiata pine is that it yields more timber or wood fiber per hectare per year than many other timber species. This makes it a great use of our land mass and a very efficient producer of high volumes of wood fiber. In addition, we harvest the trees every 27 years. And what this means is that within the lifetime of our product, at least one tree has grown, making this an infinitely renewable building material. Radiata pine stores a lot of carbon. And in this graph, you can see the relative amount of carbon that radiata stores compared to many other species. we have an environmental product declaration that shows this data. So we have this wonderful renewable base material, but we're wanting to create a product that can compete with high-performing old-growth species. To do this, we have developed a process that is specific to our radiata pine using what we call heat tempering, or otherwise known as thermal modification. It's a three-step process. The first step involves heating the wood gradually up to 230 degrees Celsius. The second step involves holding the wood at 230 degrees Celsius core temperature. It is this point where the modification of the wood happens. From our research, we have found that 230 degrees Celsius is a critical temperature in order to reach the required durability for exterior use in this particular species. At this point, the wood is at 0% moisture content. So the third phase of the process involves reconditioning the timber using steam and bringing the moisture content up to around 7%. This is roughly half regular kiln-dried timber. So at the end of the process, we end up with a timber that has had a permanent change in the chemical and physical structure of the wood. It increases the durability class of the wood from class 4 to class 1, according to European standards. And it also increases the dimensional stability by up to 50% compared to kiln-dried radiata. And you can see the radiata pine going into the kiln before treatment. These kilns are monitored remotely by computer so that every batch has a consistent quality going through the process. So we've changed the properties of the wood at this point, but if you recall, we're wanting to provide a high-performing alternative to old-growth timber. So this means not just durability, but even more stability in terms of dimensional performance in service. So to do this, we have developed a patented proprietary process to orientate grain vertically in every board that's supplied. To do this, we take predominantly flat-sawn, thermally modified radiata pine, and we laminate it by applying a polyurethane glue line to the face of the boards. This then allows us to create blocks of timber that we can put through a saw perpendicular to the glue line and then create all different shapes and sizes according to the product that we're producing. The appearance then becomes one that is very similar to old-growth western red cedar and tropical hardwoods. But because of this vertical grain orientation, we also get 50% better dimensional stability when exposed to moisture outside. The other great thing is the appearance is very aesthetically beautiful, and this really allows us to offer a viable alternative to old-growth timbers. So we've solved the problem of providing an alternative to old growth, but we're still facing the challenge of fire compliance. And this is where Abodo Varro comes in. We consider this the new standard in timber innovation. This is the only ultra-durable, fire-compliant timber available as a complete coated, tested product range, all from one trusted manufacturer. But why Varro? The question around fire compliance really has become more prominent with the advent of the Grenfell Tower tragedy in 2017. This resulted in a mass loss of life, but it also caused building authorities around the world to start questioning both the standards as well as building materials that were going into buildings. And from here, our customers started to ask, what is your solution? Then with climate change, we have an increased risk of bushfires and wildfires, and we're seeing in places like Australia, California, and Europe, more and more tragedies that are occurring with mass loss of life and property. Thirdly, with population growth, people are starting to live closer together and living higher up. And so with this comes the need for fire-compliant materials in these situations. And the final point is that with climate change has become a growing awareness and demand for low-carbon building materials. And timber is a great solution in this regard. So this set upon us a challenge to solve the problem of how do we embed fire safety into timber, but ensure that it stays there during the lifetime of the product. And this is where the Abodo Varro project started. So the premise of the project was to create a fire-compliant timber that performed over time and that the fire retardant did not leach out of the wood in service. To do this, we proposed that we would use a full cell pressure treatment to impregnate the wood with a thermosetting resin and then heat cure this into the wood cells so that the fire retardant would not leach out when exposed to water. So we started this journey 10 plus years ago, and over the last 5 years have engaged with testing laboratories and collaborators across 4 continents to really rethink how we are going to present timber in high-risk applications. And you can see here on the bottom left a photo of the small-scale lab testing that we started with, which allowed us to create small sample sizes that we could then put into a bench scale lab test and start to build up confidence in the performance of the product. On the right, you can see scaling up into a pilot scale pressure treatment plant, and this allowed us to treat timber in longer lengths, which then allowed us to test to the larger scale tests that are required in some of the jurisdictions such as Europe and USA. At the end of this development process, we came up with what we call triple modified timber. So here we are really transforming the timber at a material level far beyond just a surface treatment. So to produce Varro, it's a 3-step process. We start with our Vulcan heat tempering process where we thermally modify and orientate grain vertically. The second step is where we impregnate the timber using vacuum pressure with a resin and fire retardant solution. Through this process, we get full cross-section penetration of the treatment. This is very important when we are talking about exterior use timber, as well as the ability to remachine the timber after it's been modified. The third step involves applying high temperature to cure the resin into the wood cells. What this does is permanently fixes the resin into the cells of the timber and binds the fire retardant into the process. So at this point, we end up with an ultra durable and highly leach resistant timber product. So this slide shows the fire triangle, and what we have here is the ignition source, the source of or a burning source, a material, and then oxygen. These are the 3 elements that are required to generate a fire. The way that Varro works is that during the initial charring of the surface of the wood, nitrogen is released, and this in turn blankets the surface of the wood, and then so in turn doesn't allow the flame to continue to burn. And this is what limits the flame spread across the face of the wood. So looking into where we started on testing. Testing is really the critical piece in this product, in that it demonstrates our compliance with the various standards around the world. So we started with the ISO cone test, which is an ISO 5660 test, a bench scale test that takes small samples of wood, 100 by 100, and then creates a classification from this. And this really allowed us to start building up confidence in the material and that the treatment we were applying to it at different levels could meet the various standards that we were looking to achieve. The other great thing about this test is it's recognised under the New Zealand and Australian standards. And through this testing, we achieved Type A cladding for New Zealand and BAL 29 for bushfire use in Australia. Once we'd started to build this confidence in the product, then we went to a larger scale test methodologies. This one here is the ISO 9705 full-scale room test. And here we achieved Group 1S for New Zealand and Group 1 in Australia. And this is a spread of flame test that is recognised for interior applications in these two countries. For the EU and the UK, the EN 13823 single burn item test, or SBI test, was used. This is a slightly smaller scale test, 1.2 metre high wall in a corner configuration. And through this testing, we achieved Class B according to EN 13501, which is the highest classification for wood. We also achieved this classification after pre-weathering according to EN 16755. And I'll talk a bit more about that in a minute. This testing was conducted at RISE in Sweden. For the USA, this country and market recognises a slightly different test method called the E84 tunnel test. And you can see here, this is a horizontal machine that has a 24-foot long wall section in it that then has a heat source introduced at one end. And in this testing, we did the 30-minute extended test that is recognised in the California WUI standards. And through this testing, we achieved Class A and with a flame spread index of 0. Again, this testing was conducted before and after pre-weathering at QAI in California. So while it's relatively easy to actually pass these tests before the leaching process, but the real challenge was passing the test after the pre-weathering step, which is often called up in most of the international standards if you're putting the wood into an exterior application. The reason this is challenging for fire-treated timber is that many fire-rated chemicals are hygroscopic, which means once they're exposed to water, they can leach out of the wood. So we wanted to be very clear that our product would perform at the highest level after being exposed to the weather. So there's two main methods that are recognised around the world. The first is the ASTM 2898, which is a machine weathering method. And you can see on the right there's the machine that's used there. In our case, we actually weathered full-length boards where possible. So 1.2, 1.5 metre length boards, not small pieces. And then we conducted the test. Then we have a natural weathering. So EN 9273 is a natural weathering standard. And you can see on the left there, these are full-length boards that are put into an accelerated weathering situation outside. And then we are testing the boards after that weathering process. And through all of this testing, we built up a very high confidence in the ability of this product to maintain its classification after weathering. So coatings are notoriously difficult to apply to many fire-treated timber products. So we wanted to be sure that we had a fully tested combination of our coating with the base material. And so here's a test. You can see there's a photo here and it shows the Varro on the left. The first 3 boards are protector coated boards with our semi-transparent wood stain, and then the 4th board is left uncoated, and this is weathered for 18 months. And you can see uncoated, the timber weathers to a nice gunmetal grey, but you get very good coating performance on the timber, compared to on the far right is a competitor fire retardant which has been impregnated into our Vulcan product and then had the same coating applied. And as you can see, early failure of the coating is occurring. So we feel it's very important to test the combination of coating and base material to give customers confidence that in the long run they're not going to have any problems. So the Varro product is available in a range of colours in our protector range, but because the wood maintains its natural tactility and machinability, it can still have the same bandsaw, dressed or brushed finish applied to the surface of the wood. And this is great because you still get that natural wood materiality of the timber that everyone really wants to maintain. So what we found through our testing is this process imparted more than just fire performance. So we conducted testing to European standards for in-ground testing, and the product performs to a Class 1 durability standard, otherwise known as Use Class 4, similar to old-growth tropical species of high durability. And this has really allowed us to offer an extended 40-year durability warranty for the timber. Similarly, the properties of the wood have changed, so the density is increased from 420 kgs a cube up to around 680 kgs per cube. This makes it more resilient and gives it a higher level of hardness. We conducted termite testing against the Formosan termite and found that the Varro had excellent resistance to this termite. This is one of the most aggressive termites in the world. As you can see on the right, untreated radiata pine fully destroyed and the Varro remaining intact. In terms of environmental compliance, Varro is not classified as harmful to health or the environment under the European REACH regulation. And because it's also a water-based treatment and does not contain any heavy metals, halogens or sulfates, which are typically often contained in traditional fire retardant treatments. And in its final form, the product is non-hazardous. In terms of emissions, we have tested to a number of different standards around the world. The Japanese A1460 standard, where we achieved E0 or F 4-star. We tested to the European standard EN7171 and achieved E1, which is the highest classification. We've also tested to the California Department of Public Health standard, which is arguably one of the highest standards for VOCs, and there we passed. In terms of the finished product, the focus of this product is really around exterior cladding, screening, and internal lining. But one of the great things about this as a base material is because we're getting full cross-section penetration of the treatment, we are able to supply our distributors with rough molder blanks that can then be remachined, subject to some limitations, to create all different shapes and custom profiles for customers. Screening products could be used both externally for rain screen, but also internally. And interior paneling, walls, ceilings, and soffits, we have both an 18mm and also a 10mm thick product. So in summary, what we've created here is really a product that redefines what timber can be. You've got fire performance, durability, and full product level design so that we can really give confidence to you as designers, engineers, and builders that this product is going to perform in the long run with confidence, safely and beautifully. Next, we'll go to a roundtable that Sarah and I conducted with Simon McLean and Martin Feeney, where we talked about where fire compliance meets reality. Enjoy. Well, welcome guys to this Fireside chat, where we're going to talk about where fire compliance meets reality. And I guess the purpose of this conversation is just to really do a bit of a deep dive into some of the universal frustrations that may be experienced between where we have a compliance path that's specified in our practices, and then when it gets executed on site and what the implications are there in the real world. So I thought we'd have sort of a bit of an honest and open discussion in terms of the New Zealand context, particularly where we're operating. I thought let's just start with opening and talking about the ideal versus the build. Okay, so in principle, compliance frameworks are pretty robust. We've got standards that we're working to. So where, in your guys' opinion, do things break down in reality? Maybe we start with you, Martin, and get your perspective.
Okay. Fire design and the transfer of fire engineering information to the construction site is actually quite a complex process. Our building codes specify a certain level of performance, and the fire engineers generally understand that. They generally understand what sort of systems are necessary to be put into buildings to achieve building code compliance. And often that involves quite a high degree of technical understanding, technical analysis, engineering judgment, and that's transferred into a description of a solution which needs to perform in a certain way. That information then gets transferred into sketches and documents which are passed around to a design team which are not fire experts. And so they need to interpret what the fire engineer has described in terms of systems and performance into a specification of items and elements and constructions which form a specification for someone to build from. And so just about every step in the process, from understanding compliance with the building code in a fire sense through to specification of elements that get built by a builder on building site, goes through a process of interpretation and re-specification that often dilutes the accuracy of the information. Sometimes it distorts it. It's really hard to keep it accurate and technically pure right through the chain of command, from fire engineer to generalist designer to contractor to subcontractor. And through that process, you end up often with a level of distortion.
Yeah, really interesting. And so from an architect's perspective, Simon, what's your perspective on this?
Yeah. Well, as Martin says, we're a step in that chain, and sometimes you fear there's almost from one source of truth, let's say, being a fire engineering design. From there, is there this risk of it almost dispersing into many documents? The door hardware is located somewhere in this pile of document, but it's very important on that particular door that it complies with what the fire engineering design needed, and so we're in the middle of that process. We're working on complex jobs where it's not just cookie cutter solutions, and we're a part of being a very thorough review of that fire engineering design and applying it to our documents, and then often looking to coordinate as a lead consultant with other consultant packages as well, and from there to the contractor. And it makes sense. The process makes sense, but it's an interesting one. It's almost like the fire engineering report sometimes has an interesting status once it gets into the contractor's hands. Either it's all in my documents or it's not, and there's a problem.
Yeah, I think that's quite common. The expectation of the people who need to build things or need to specify things and put things together, their interpretation of the documents can be different to what the authors intended when they wrote them. And sometimes that's an area where you get a little bit of a disconnect between what someone thinks they need to build and what the intention was at the beginning when the documents were created.
So you were saying part of the documentation from fire engineer is the system, or there'll be drawings, so there's the report, there's also sketches and drawings as well. So will the fire engineer design a system in terms of the wall makeup, and will you be identifying what each of those individual components need to comply with, or will there be specific items you'll give? Because there's the difference between, you need an item that complies with X standard, with X testing, so then that leaves open that interpretation, as opposed to going, here's a specific doorknob that complies, that has done the testing, that the architects can then use.
No, you've latched on to exactly one of the key issues. The fire engineer is typically describing performance levels for various elements. So in fire, certain elements like floors and walls and fire separations and doors and windows might need to achieve a fire resistance rating, or they might have to resist the spread of flame in a certain way. And so the fire designer is typically writing about those performance requirements without actually specifying a particular system. The fire engineer might not be too concerned whether the wall that needs to act as a fire separation is built of masonry or concrete or plasterboard or lightweight concrete. The choice for the selection of the elements is usually left over to the design team. Often the architect is the principal designer of those sorts of things, because the elements themselves might have to achieve a range of performances. A wall might have to be acoustically separated, a wall might have to resist certain forces. It needs to be structural or non-structural. Exactly.
All the other parts of the building code.
Yes. So the fire engineer is typically one step back from that level of specificity about particular elements and particular systems. And so the specifier of those elements, whether it's a structural engineer for the floor system or an architect for the wall system and doors, they end up having to choose elements which meet the performance requirement that the fire engineer has talked about. And so that's where there's that level of interpretation about, I need to find a system that achieves what the fire engineer has asked for, but it might also need to achieve a whole range of other performances.
That's how tricky is that in reality within the practice when you've got, because architects often, like a generalist, right? You need to know, well, quite a lot, but about everything of the building, all parts of the building code and every part that goes in together. But when you're doing something like this, which, I mean, the risk is so high, that risk of failure is, is catastrophic in some instances, I suppose, if you get it wrong, right?
Yeah.
Do you have people within your practice that have schooled themselves up on the fire code more so than perhaps other areas, for this reason, for interpretation, or people that work on these particular projects? Like, how do you deal with that in the architect?
Yeah, I like that word generalist, mostly because Pip Cheshire, the founder of our firm, he always said architects might be one of the last generalists in our industries, and that's part of the challenge and part of the joy, that you are trying to know a little bit about a lot of things across the process of getting a building built, and so we naturally, people in any practice, their strengths shine, and some people are better at things than others. But in short, no, we don't have people who try and specialise more in say fire design and engineering. Yes, some people are a bit more technically stronger in any practice. But yeah, well, maybe this might follow in other questions, but the complexity spirals in our industry at the moment. In any one makeup, we touch on exterior walls is a really easy one. There are matrices being generated that assign different consultants responsibility to different code clauses across each element in that wall. This really is a matrix. It kind of, makes your brain hurt to start with.
It's quite complex quite quickly, doesn't it?
Yes.
Yeah. One of the experiences that we found is that experience matters a lot. So the people who are experienced with this process of interpreting a fire designer's documents and translating that into good specification, the people that are good at doing that generally have many fewer problems in compliance approvals and on site because they understand the importance of that translation. They know what to look for and they're aware of what the weaknesses might be if they don't get that specification correct. And I think that's why we see a range of good and bad experiences across the industry with fire compliance. Teams that are less experienced are more likely to make mistakes or misinterpretations, which then just flows on to problems on site later.
Yeah, look, why don't we just take a little bit more of a detailed look at critical failure points? You guys have just touched on that, but I'm interested to understand your point of view on specification versus substitution on site. How often does it happen? What are the problems around that? And then also the misinterpretation of the specifications in terms of fire ratings and systems and how that gets translated into some of these substitution decisions. I guess the big question is, at what point in the design to build pipeline do you see the biggest risk? And is that on site or is that during design?
Depends a bit, doesn't it? In my experience, it depends on the level of care that's been exercised in generating the construction documents in the first place. And by that, what I mean is if the design team knows where the challenging construction points will be and looks out to detail those areas with a reasonable degree of care, and in particular with either a contractor mindset or with contractor input, then that collection of information that goes onto site is much less likely to be less likely to involve a range of substitution because some of the key problems and issues have already been thought about. The areas where we find most requests for substitution tends to be when the contractor starts building something and either they realise this is really difficult to build, I'd like to build it differently, or this is very expensive to build, I'd like to use different systems because there are less expensive options available. And that's where most of the requests for substitution come from. So the more those sorts of decisions or thinking can be brought forward into the design process, the less likely there is to be substitution later on.
That's an interesting point you brought up, which is early contractor engagement.
Yep.
How often are you seeing that actually happen now? Is it common or more common than it used to be?
Yes.
More common than it used to be?
Yeah, I think particularly in this country over the last 5 to 6 years, it's become more common. That might be because over that time there was a little bit less just cold, hard, open tendering, and you're a little bit more inclined to lock in a contractor that you wanted to work with earlier. Certainly that's been the experience of our firm. Yeah, and it's very valuable.
But where do you see the key risks, in the specification and execution process?
I think our practice has seen less substitution risk arise on our projects. Maybe we're just really controlling. I don't know. But there are always pressures in the industry, cost pressure, fee time pressure. The best examples go well. If you're not given the time to do something properly, then there's more risk of it being unknown on site or out of your control. Because doing a really thorough job on complex situations takes more time, I think. So the best teams get it right, but time's a really valuable commodity for anyone who's potentially fundraising to try and get a home for their organisation or something. So yeah, there's different situations.
And how do you find the interaction from a supplier's perspective? The interaction, how important is it that the supplier is engaged early in interacting in the process? And how does that manifest itself in a successful delivery?
Look, it's really important. It's a key part of it. And we are are keen to lean on their suppliers and get as much help as we can. Often that's like anything. Often that might be a panicked phone call late in the process when you realise you haven't quite, got a solution. So we always appreciate that help. And I think too, suppliers. I often think to myself, suppliers should be really upfront with architects. Sometimes I wonder if the architect rings and it's like, yes, no problem, and then the final fine print, or when the contractor rings, maybe it's a slightly different response. So, but yeah, funnily enough, the architect has to know what questions to ask, even of suppliers, I guess, to drill into something that might be a critical issue in any component. Yeah.
And just on that point, I think that's a good point. I think the industry is better, and the specifiers are better at asking suppliers the right questions. I think in the past there's been either a lack of understanding of how important it is to ask some of the right questions about performance of systems from the suppliers, so that if there's a need for substitution, or even if there's just some curiosity about using a different product, that they understand what they're getting. And we're noticing that the suppliers now are much more aware that they're likely to get a question around fire performance, for example, about the way that their materials react to fire, whether it's for fire resistance or spread of flame or combustibility and those sorts of things, because they know someone's going to want to ask that question, whether it's for the initial specification to check suitability, or whether it's down the track later for substitution. One of the first questions will be, if I'm going to substitute product B for product A, is it going to perform in the way that product A was asked to be performing?
Yeah. As a supplier, I think we have, I think suppliers, manufacturers, suppliers, whatever they're doing in that supply chain, have their responsibility is to be the expert in their product, to then help the generalists who are trying to interpret this. That is our responsibility. So, and being the expert is being very clear on what the scope of your product, your service, your whatever that is, the limitations, like the scope includes what it can do, and what it can't do is often more important than what it often can do as well. It's very important to be able to your point, be able to say yes or no, or it's not going to, sorry, it doesn't comply, or it won't achieve in this particular context, it's not going to work, and that's quite a high level of understanding and technical knowledge in the supply from that supplier as well to have that. Absolutely.
And I think particularly in the fire safety field, as a result of the Grenfell fire in London more than 10 years ago, there's now much more attention paid to the care and quality of information related to things like fire testing and product specification and product performance, so that everyone understands, both the supplier and the receiver of those materials and systems, they understand the scope and limitations of the testing, but also how the system can be used on site and in what particular way.
Yeah, absolutely. That's amazing. Grenfell's still being talked about, isn't it, 10 years later?
Well, it's good that it's created this closer attention to quality specification, quality performance, and thinking about the use of materials, and in particular some of the weaknesses around substituting materials without asking all of the right sort of questions.
Yeah, that's right. Yeah.
Okay, let's move on to accountability and risk, because at the end of the day, we're talking about lives here and trying to save lives when we're talking about fire compliance. So when something goes wrong, where does the responsibility land? And has the industry become more risk averse? You just touched on the Grenfell disaster, but has the industry become more risk averse, and how has that really affected the complexity of the specification and build process? So probably two questions there.
A couple of questions there, yes. Yeah. I mean, I think things do get complex quite quickly if one seeks a source of blame or direct accountability for problems, because, as I described earlier, the chain of information transfer goes right through the design and construction phases and involves many parties. It starts with perhaps the most technically careful person, which would be the fire engineer, and then that gets transferred through a range of different other designers and specifications and documents through to the contractor who needs to interpret and then build. If something goes wrong, there are many parts to that chain which could have broken down to cause the problem. Was it incorrectly constructed? Was it incorrectly specified? Was it incorrectly used in a certain way in a certain part of the building? Or was the designer at fault by asking for the wrong thing in the wrong place? Or was the fire engineer at fault for not checking or specifying certain levels of performance? So it can be quite complex quite quickly, and it becomes very difficult to assign direct accountability, which means that kind of all parties have some level of accountability for some aspect of good fire performance, which I think is now everyone's a bit more aware of that than they were in the past. I think for other disciplines, and I think previously it was easy to point the finger at particular parties and say, you should have picked this up or this was in your camp, without realising the complexity of information transfer that actually says, no, hang on a minute, there's a collective responsibility here, starting with performance, going right through to product specification. That means everyone needs to be understanding how their role contributes to the successful outcome.
Yeah, I mean, one of the results of the Grenfell disaster was that there was a much, building authorities started to take a much closer look at this sort of stuff, right?
Yeah.
And
being much more careful about who's making decisions for change.
Right.
If someone wants to change something, are they the right person? Do they know enough about what they're asking to change to be in a position where they make a good decision?
Right. And I mean, with that, there was obviously a whole lot of changes made to building codes, standards. Like you said, behaviour probably changed. Do you guys feel that there's been a positive change in that way? Do you feel that the behaviour has changed in a way amongst the different parties, whether it's suppliers, fire engineers, architects, building owners, in a way that has become, more considered in a way that is building safer buildings now? Do you feel that there's positive change there?
Yes, I think so. I think now all of the parties are much more aware of the importance of correct specification and understanding performance and understanding different performance levels, which is a good thing. People are more attuned to the fact that what they ask for and what they build is important, and changing it is a challenging process. And I think the regulators are latching on to the benefit of having a well-structured system that comes from all of the parties understanding their role in the chain and having relatively tight specification around performance of materials and systems that might have not been so quite carefully controlled in the past. That's definitely a good thing. One of the downsides of that process is that it makes it harder to make a change, a necessary change, that might be not really affecting fire performance, but is caught up in a system which assumes that a specified system is the only way of achieving adequate performance, adequate outcomes. And so if someone wants or needs to make a change to the system, sometimes it can be more difficult because the very process that delivers a confident outcome also makes it much more difficult to make a suitable change, because one then has to establish, if you're going to make a change and use a different system, is it going to perform in a way that still complies with the overall performance requirements of the code rather than necessarily the specific performance of that particular system?
How do you feel about this risk business, Simon? Where does that fit in your world?
I think, as Martin said, it's spread across the entire chain. We've all got our part to play. I think we are typically involved in projects where everyone's doing full design, so that I think that's a good thing. And so that uncertainty where elements become only partially designed or design and build or other modes of operating is a little different. We have less experience with that. I think there's a lot of upfront discussion about risk now between contractor and client, and because it's logical that some aspects of risk, can be shared depending on how you structure agreements or contracts. And if that's agreed up front or understood, then I think that helps. Just everyone have some confidence to move forwards. Yeah.
Martin, Simon, thank you very much for coming in today. It's been absolutely fascinating. We really appreciate your time.
Thank you for the invitation.
Hey, look, thanks for attending today. And I'm just going to answer a couple of questions that have been sent through. We've got about 9 minutes. So the first question was from Alvin, and she's asking, can you comment on the suitability of Varro for doors and windows? I guess the end use application for this product was not intended for that. That said, there's no reason why it couldn't be used in that sort of application, but it would need to form part of the testing of that particular system as a fire door, or otherwise could be used as a surface material to go on the outside of a door where a Group 1 material was required. But effectively would form part of that system to be tested. And that leads on, there's quite a few questions here around the system-based approach versus a material approach. And so what we're going to do is we're going to collate some of these questions and sort of come up offline with a sort of more meaningful response. But I guess at a high level, our product is, as Sarah said, a tested material. It forms part of a wall system. And I guess there's a couple of ways that you could meet compliance. One would be take the acceptable solution route. So using what was stated in the building code as a path for compliance. The second would be to incorporate our material as part of an existing proprietary wall system with the likes of, say, for example, Jib, where they've got an FRR wall system and then it's calling up a Type A cladding to go on the outside of that. Then we could form part of that system. There was also a question around compatibility of connectors and gussets and things like that. Again, the same approach would be taken, and we've had advice from the likes of, say, Jib on this, where they have said they have a tested component within a fire-rated wall. As long as our material conforms to the test standard, which is Type A, then it would be acceptable to use with their proprietary system. So hopefully that sort of answers that. I think there was some mention around the fact that ultimately there would need to be a fire engineer to sign off on the approval of these sort of decisions. And we would tend to agree with that. From our perspective, where we play our part is as a tested material. So how it fits in terms of the overall system ultimately probably does need an approval process that it conforms with the building code. So tend to agree with that comment. There was another question around declare label. We don't have a declare label for this product. It does have some added formaldehyde in the process, and so it would be that is a red list chemical. That said, in its finished form, the product is non-toxic and inert. And there was a question around what are the components that go into this fire retardant chemical makeup. It's a nitrogen-based salt that is non-toxic, that is combined with a polymeric phenolic resin, and then that's cured into the cells of the wood. And at that point, the material becomes completely inert and non-toxic. In terms of handling it, in terms of health and safety, it'd be the same precautions that you would take when handling normal wood. In terms of when you cut it, you'd be wearing a dust mask, gloves, and goggles. to protect your eyes. There was another question around cost. The cost of this product is going to be dependent on the region you're in, and also what's the end use application. But as a rule, I mean, it's positioned up at the higher end of the price point per square meter, but it will compete with typical, fire-rated composite materials such as aluminium, and sort of materials at the higher end of the cladding segment. It probably won't compete with fibre cement or materials at the cheaper end. So really it would be used in an application where people want a natural wood look. They want that beauty and materiality of wood, but they want fire performance. I've got another question here around composite products such as composite decks. And does cutting Varro release any kind of long life micro compounds into the environment that may be considered possibly carcinogenic, similar to microplastics? Yeah, I guess at the end of the day, it does have a polymer in it. And if you were to have the sawdust coming off the cut, then you'd want to contain that and put it in a bin. It will eventually break down in the environment, but it will take some time. So while it's not plastic, it does have a resin in it, so you do want to contain that if you can. But like I said before, it's not toxic, but the wood dust, any wood dust, if you breathe it in, can be carcinogenic, so you should wear a dust mask. All right, guys, I think that's about time. So look, thanks a lot for coming onto this presentation. Like I said, we're going to collate up a lot of these questions and look to sort of put more meaningful answers to some of them and send them out, particularly around the systemization. I think that was a big topic on this one. So yeah, thanks a lot for joining, and hope to catch you guys up in the future.